Hello, my name is Jordan Garrity. I'm going to be a junior this fall at Purdue University. My major is Machine Systems Engineering in the ABE department.
Hello, my name is Stefan Jane. I'm going to be a senior next year. I'm from Stony Brook University, from the State University of New York, and I'm a mechanical engineer.
Basically, the background of our project was there isn't really a coupling mechanism right now in the fluid power, background with digital on-off hydraulic valves. So it's really hard to create something with high velocity and high flow without using some sort of digital background. So what we have here in our test stand is a MR fluid, which stands for Magneto Rheological fluid device, that basically when you apply an electric current, the fluid turns to a gel, and we use that in lieu with a moving mass. So when you move the mass in the de-energized state, it should move just basically up and down because there's nothing blocking or creating friction in the system. But when you apply a magnetic field, the MR fluid becomes a solid, and that creates a frictional coupling mechanism that can slow the moving mass, and we can control that via D-Space in our lab program to sort of turn on and turn off the electric current to slow the mass or start it back up. And so future use of this project will be in an actual hydraulic valve that will be opening and closing a valve. So allowing fluid to flow through and then stopping it to not allow fluid to flow through, I guess.
Yes, the best thing about the MR fluid is that when there's no magnetic field, it's completely a liquid. You see that I can push it and do anything that I want with it right now. But once I put the magnet right next to it, it suddenly turns into a solid. Then I can no longer push it to this area anymore. I can pull it out, see what's happening, and then once I put it, it turns into a solid. So that's the same thing when we use it as a coupling mechanism. Once you see, if you look here, this is the fluid-based Magneto Rheological fluid right here. And one thing we didn't expect with that is that we thought that gravity was strong enough to overcome the viscous effect of the Magneto Rheological fluid. But when we started the experiment, we couldn't push it down because the friction created by the fluid was too strong, it was too high. So we had to design a little fluid power circuits in order to pull the moving mass up and down. I was focused more on the designing aspect, like every mechanical thing that you see behind the project, like designing the fluid power circuits, designing the container and everything with the moving mass, and the placement of the electromagnets. And Jordan was more on the software and electronics behind it, so that we can collect the data and everything.
So you start with what we're using as a pump. It's just a bike tire pump to pressurize the system. And we start at zero, with the lasers at zero, at the bottom of the displacement of the moving mass. And we turn the valve on to power the cylinder to pull the moving mass up. And so that's at the top stroke without any electricity. And if we were to turn the program on, that measures the displacement. We've tuned it to when the laser hits 2 millimeters, so when it's accelerating from 0 to 2 millimeters, at that time, 2 millimeters, the voltage is applied, and 0.6 times 10, so 6 volts come from the D-Space data acquisition panel to this circuitry that we designed, and that turns the relay on. And basically all the relay is it's a switch that allows current to flow from this constant 12-volt supply system that feeds all the way over to our electromagnet inside this moving mass. So within a matter of 2 millimeters, it's turned on, and the fluid inside this mechanism between the moving mass and the electromagnet, which we call an MR fluid gap, is 100% solid. So that's what's breaking the system and what stops it before its top stroke. And some different test results that we experimented with is that we could adjust the gap. We put spacers behind this electromagnet here, and they're basically just small washers that we can adjust the gap between the moving mass and the electromagnet. First we started out at 1.5 millimeter gap between the moving mass and the electromagnet, and then we removed a couple of washers and made it 2.2 millimeter gap, just to kind of see the difference between what a smaller gap does versus a bigger gap, because initially we weren't 100% sure with the bigger gap maybe that would make more of a solid fluid, so maybe that would break it more. But our results concluded that with the 1.5 millimeter gap, the braking force was a lot stronger than the 2.2 millimeter gap.